Okay, so yeah, I'm currently a postdoc here at Stanford. I'm also a technology fellow at the Electronic Frontier Foundation. So I'll be talking some about my academic research and also about some of the work I've done at EFF to promote secure messaging tools to try to help people understand different secure messaging tools and what properties they provide. So the context of all this really in the last couple of years, we have some good evidence from, I mean, there's tons of anecdotal evidence, but there's also hard evidence from talking to people that people are much more concerned about surveillance than they used to be.
Yet they use Facebook.
Yeah, but you know, this shows up both in surveys and also from the EFF's perspective. After the Snowden revelations, EFF got tons and tons of queries from all sorts of different organizations. They said, "What can we do to protect our communications from surveillance? What can we tell the dissidents that we work with? What can we tell the journalists that we work with about how they can protect their communications?" So this has been a really, really big topic. You know, I think there's some evidence that people don't totally understand what the real threats are. If you look at data from this same survey, people are much less worried about using a landline phone than they are about sending email, using chat or IM, which is what I'll be mostly talking about today, is sort of chat or IM or messaging tools. So, you know, people don't exactly understand what's going on because they still think that using a landline is secure here. It's really not. I mean, this is probably the least secure of all the communication channels here. I would say, you know, using a plain old telephone system is basically the worst you can do. There's no encryption, or there's no real possibility for end-to-end encryption. So if you're worried about kind of government surveillance, this is, you know, not a great place to be. So I'll come back to this theme later, that users don't exactly understand what they're afraid of or what security properties different channels have. But for now, I just wanted to say that people are definitely more worried about surveillance than they have been. So the high-level bit that came out of the Snowden docs that was positive is that there was no evidence really anywhere in the docs, besides a couple of things kind of circumstantially that people have patched in. There wasn't much evidence that you know, the main cryptographic protocols we have are actually broken. In a few places, there was actually evidence that NSA was frustrated when people were using PGP because they didn't actually know how to decrypt and read the messages. So when people use cryptography, from everything we know, it still works. It doesn't appear, you know, even that NSA has a magic way to break the good cryptography that we have when it's actually used. So the problem, of course, is that it's famously really hard to actually use cryptography. So how many people have used PGP? Okay, so most people, so Henry's a holdout there.
It is hard to use.
Yeah. So I'll just show you a couple clips from this this video, which I think, if you've never seen this video, I think really drives the point home really well. But this video was actually made by Edward Snowden and given to Glenn Greenwald, the journalist that he was working with. And Glenn Greenwald said, you know, at the beginning of his conversations with Snowden, he really didn't know anything about encryption or security, so he had to get up to speed to rendezvous with Snowden and kind of serve as his liaison to the public. So you'll notice this video is going to be 12 minutes long. So, you know, right off the bat, if it takes 12 minutes to explain to the public how to use a piece of technology, that time budget is kind of way too long.
It says, hey, here's
so you can see. So it's kind of a fun video. Snowden actually used some voice masking technology here, which is why it's hard to recognize his voice. That was by design. So anyway, he spends some time kind of talking about the threat model. And then he starts walking through how to actually use PGP software on Windows. And it's really a mess. I mean, you can kind of look along the bottom of the screen here, at the beginning of the window, it was just, at the beginning of this video, it's just the web browser that's open, and it kind of slowly builds up. By the end of the video, he gets, almost his entire system tray here full of applications that he's running. So there's like a lot of stuff going on at this point right here. He's now creating keys, kind of 5 minutes into it. And there's one point, let's see if I can jump to it, where he's actually, copying keys. He's using Notepad. He's copying and pasting the key in ASCII just to import it from the tool that created it to the email client that's going to actually use it. There's parts in this video where he says, you have to hit that checkbox or else the whole thing is insecure. There's kind of gems throughout. But it's a pretty clear sign that this PGP is over 20 years old now, I guess almost 25 years old, and it's never really grown into a technology that people were comfortable with using. So we have a lot of evidence for that claim beyond just one video. The video is more fun. There are also a lot of academic studies in the lab. They brought users in and given them tasks to say, can you install PGP software? Can you communicate with these people? A lot of people just don't do it at all. It just blocks their communication. A lot of people will, in those experiments, they'll inevitably send things out in plain text. They'll do things like, encrypt to their own public key and then send to somebody else. So, we have pretty hard numbers that this doesn't work so well in practice. And if you need any more convincing, this was maybe the most fun anecdote from my time at EFF. I was working with Phil Zimmerman on a project. So Phil Zimmerman was the original developer who created PGP. I made sure the first time I emailed him that I PGP encrypted the message. And he just responded in plain text, sorry, I don't do PGP anymore. So just send this back in plain text. And I asked when I got this, I said, you have to let me use this in talks and tweet about it because this is so perfect that even the person who made this software found it too unusable to actually use. So that's kind of the state that we've been in for a while, where cryptographers have historically not devoted too many resources to this problem. There's a by now pretty famous paper that was written last year called The Moral Character of Cryptographic Work, arguing that the cryptographers sort of owe more to society than to sort of ignore and marginalize this work on making things actually easy to use. To be honest, I'm not sure this paper has really swung more researchers to get into this problem. I think it's gaining a little bit of traction, but it's been a real problem to get cryptographers, especially in the academic setting, to stop sort of, or maybe to not spend all their time chasing the next big algorithmic or theoretical breakthrough and try to make the things that we've had forever actually easy and secure for people to use in practice. Okay, so I basically told you that PGP is mostly dead. I think very few people are really even trying to revive it at this point. I mean, it's still very much alive and that a lot of people have used it, but I think we have pretty clear evidence that it's sort of not the mass market solution that people hoped it would be.
What's the largest percentage of anybody that you communicate with of messages they sent out encrypted as opposed to clear text?
You're saying in my personal communications?
In terms of anybody you've ever encountered, I've never found anybody who sent more than 10% encrypted communications. That high.
It's a good question. I mean, I guess there are some, I don't know about people, there are some email addresses that are always encrypted, but in terms of like an actual human being, I don't know. I think most people will have an unencrypted email address for sort of, signing up for accounts and maybe emailing friends, small stuff. So, I would certainly agree with your statement there that most people don't encrypt very much of their email over PGP, even if they use PGP. Okay, so the scene for PGP is kind of grim, but at the same time, in the last few years, we've had a somewhat quiet but a revolution in how much end-to-end encryption is actually happening. And all the action is happening on chat applications or messaging applications, basically software that you download on your phone that gives you kind of an ephemeral chat experience. And the two biggest ones, iMessage from Apple and WhatsApp. So each of these apps has a user base that's in the hundreds of millions to billions of users. And everything is now end-to-end encrypted all the time. So in human history, these are by far the majority of encrypted communications that have ever happened have been over WhatsApp and iMessage. Just the amount of encrypted traffic that's gone through those two systems is vastly more than the amount that ever went through PGP in its entire lifetime. So I'm. Is everything okay? Okay. So in a sense, that's really exciting, and I think the most interesting thing is that most users who use WhatsApp actually don't even know that it's encrypted. And the same thing is true for iMessage. So it's kind of completely transparent to the users that are using the app, but everything is encrypted now. In fact, until about a year ago, WhatsApp wasn't encrypted, so this is something that they added after the fact, and they were able to add in end-to-end encryption, which we saw for email as sort of this cripplingly difficult thing to use. They were able to do it without even changing the user experience. And there are a whole lot of other apps that have launched that offer some level of end-to-end encryption, including, I know it's really confusing because almost every one of these apps has some version of the same logo, which is a chat bubble with some kind of lock on it. But this is Facebook Messenger, which also has hundreds of millions of users, and this is Google's new Messenger, which is supposed to replace Google Hangouts. So Facebook and Google have sort of gotten on board the end-to-end encryption train. Although it's important to note there's a big difference in that Facebook and Google users have to actually explicitly turn on the end-to-end encryption. So they have to choose to have what's called a secret chat. Whereas with WhatsApp and iMessage, everything's end-to-end encrypted by default. You don't have a choice to fall back to insecure mode. So it's interesting that they've differed there.
Signal play in this race?
So Signal, which happens to be right here. So I'm sure a lot of you have heard of Signal. Hopefully we have a lot of Signal users. Signal, it has, the order of magnitude that we're talking is about 1 or 2 million users. So it's at least 2, maybe 3 orders of magnitude smaller. I think a good way to think about Signal is it's kind of like a Formula One car in a way. It's kind of pioneering the new technology. And in fact, Signal's encryption protocol moved from Signal to WhatsApp. So Signal is sort of more cutting edge. They're adding more features and sort of experimenting on security, but it's always going to be kind of a smaller user base because it's a security focused thing. It doesn't have as many of the features that users like for fun, kind of emojis and sharing animations and things like that. So that's how I view its role.
How vulnerable are big players to something like the Investigatory Powers Act?
So I guess the rest of this talk will be sort of talking about that a little bit from a tech perspective, from a legal perspective. I'm not a lawyer, so that's a pretty complicated question. I think even the lawyers at EFF have been thinking about for a while, and it's really not clear. I mean, obviously through EFF we were involved in a big fight over iMessage that wasn't about Apple. It wasn't about iMessage specifically. It was about encrypted devices. But I think the shortest answer is we're probably headed for a big decisive court case sometime in the next 5 years or so, and then we'll have more of a clear answer. Okay, so it's a little bit fuzzy. This is not really a technical definition, but people ask, why is there so much more encryption happening on these messaging apps than on email? There are some different characteristics here that have made this possible. For one, email is this kind of open federated system that PGP tried to build on top of, but that made it very hard. It's been hard to sort of upgrade PGP. So compatibility was always a big problem, whereas all of these chat apps are walled gardens. So they're all Yeah, they're all walled gardens, so they all have sort of one official application, so you have to use sort of the official software, and there's one server, unlike email, which is open and you can email anybody else. And then, from a technical standpoint, at the bottom here, two differences that make encryption easier. The user experience that people expect from a messaging app is that it's an ephemeral conversation, so if you lose your old messages, people expect that to happen, whereas email, people expect to stay around forever. They expect that any device, anywhere they go, they can download all their old previous emails. Traditionally, we thought of email as being purely asynchronous, that you can always send anybody an email and it stays on their server in their mailbox until they download it, whereas a lot of messaging apps were synchronous, so both people would be online, they could do a key exchange, and that makes security a lot simpler. This distinction is breaking down a little bit. A lot of the messaging apps are actually moving to an asynchronous model now for a variety of reasons, but at least initially that was something that we thought was different between these two. But I think the biggest change really is the fact that these apps are walled gardens, so it's much easier to roll out some proprietary encryption protocol and sort of update it without asking the users to change what they're doing. And without worrying about backwards compatibility, since there's basically one set of client software, you can upgrade everybody at once to use new encryption tools. So why are these apps doing it? There's a couple of different reasons. We'd like to think that the only reason that people encrypt is to do right by their users and to give them a secure experience and to maintain users' privacy. Turns out from talking to these companies through my role at EFF, I found there's two other big reasons why they're interested in rolling out encryption. One is to reduce their liability. So if you don't store a bunch of your users' messages, then you can't be hacked, you can't be liable for it. And the other one, which is really interesting, is that if you don't have to serve requests to law enforcement when they come and ask for user data, that's just a whole process that you can eliminate from your business, which is really nice. And my favorite story to that effect is a messaging app called Kik, which doesn't actually make any information public about whether or not they're doing encryption. They don't promote themselves as a secure tool. They don't commit to the fact that they're doing encryption. But if you go to their page that they've set up for law enforcement, then they say, oh, we can't actually give you any data because it's all encrypted. So seemingly their only motivation to employ some sort of encryption was just so that they didn't have to deal with law enforcement requests for data. On the other side, the sort of hang-ups that have kept Facebook and Google, the reasons why they didn't turn on encryption by default for everybody, and they made it kind of this optional mode that very few people use. Google specifically, in the last few months when they launched Allo, they said they were really excited about their smart assistant feature. So while you're chatting, the way the app is intended to work is that if you're chatting about going to dinner, the app will pop up suggestions of restaurants and things like that. So the entire time you're communicating, your data is sort of being sent to Google servers to provide these assistant services. Which get turned off if you go end-to-end. And they said that for most of their users, the users care more about having this rich experience than they do about encryption. So that was the choice that they made. A couple other reasons, being able to deal with spam. So doing content-based spam filtering becomes a lot harder if everything's encrypted. Fairly straightforward. Also sort of abusive users, if people are sending abusive messages, things like that. Much harder to police these encrypted apps. And just providing sort of the experience people want where they can have all of their past communications stored on the server, and they can search, they can sort of sync with any new device. All of those things become vastly harder once you encrypt everything. Yeah?
Backup of the messages is issue, like if you drop your phone in the sink and it gets fried with Signal, can you get all your old messages back, or are they gone for good?
So it's a little more complicated now in Signal because they have you can sync on multiple devices, but by default, no. So like if the simplest case, if you just have one device and you install Signal, and then you drop that device in the lake, then your messages are gone. That's actually that is a big issue with iMessage. So there's a big caveat to the fact that iMessage is encrypted, which is that by default, all of your iMessages do get backed up in plain text to the Apple server. They're encrypted with your Apple account ID, so they're basically password encrypted, which is kind of weak. But a lot of the how-to guides on how to use iMessage securely make a specific point that you should disable backups. It is kind of funny because they've encrypted everything, but then they back the plain text up. But you can turn it off if you want to. Yeah.
And encryption, by that you're talking about the channel itself. The two endpoints are still vulnerable.
Of course, yeah. So that's all crypto is ever going to get you, is sort of the data is only accessible at the endpoints.
Just that it's important that that be clear.
Absolutely. Yeah.
Because breaking into a server may be more difficult than doing into a endpoint way out on the tree, but either one is still important.
Probably, that could be true, but at least the hope is that breaking into endpoints doesn't scale as well. So if you want to do mass surveillance, much easier to do it at the server than to try to compromise every endpoint. So that's the hope. But obviously that's a caveat to everything, is that if users can't have a secure endpoint, if they don't have the legitimate software to do the encryption, then nothing's going to work out. Okay, so the main technical weak point, which I'll spend some time talking about, is how users actually get the right key to do encryption. So the way all of these apps work right now, they have a centralized key server. So when Alice signs up, she uploads her public key to the key server. When Bob wants to send Alice a message, he just asks the key server for Alice's key. And obviously, if the key server is malicious, the key server can tell Bob that Alice's key is something else, at which point the server can man in the middle of the traffic, to their heart's content. And one of the difficult things here is that for all these apps, again, the key server also sees all of the traffic, because all of the communication gets funneled through central servers. There's no peer-to-peer communication happening here. So they're in a very, very good position to man in the middle all the traffic if they want to. So the security of the whole system relies on Alice and Bob being able to somehow communicate, not mediated by the key server, to ask if Bob has the right key to be encrypting to Alice. So solving this problem is the main security challenge that we have to make these apps actually secure. So if you've used Signal or WhatsApp or lots of other apps that have some version of this, the classic answer we've had is that you do key verification. So you look at a fingerprint of your key, you read it out, you compare. Maybe you do this in person. Maybe you trust some other channel. But that's the idea. Signal also supports a QR code way to do this if you're in person, but pretty painful to actually do this. How many people have actually verified a key in Signal or another tool by hand? Yeah. So a couple folks. Yeah. So pretty painful. There have been some research efforts to try to make this more usable, or at least more fun, by showing the key in a more interesting way. There's a library for expressing these keys as random art. This is one that does robots, so those two robots represent different keys. There's one that does it with unicorns. This thing on the bottom here turns your key into a random poem. For the most part, this hasn't really been backed up by good research saying that this is actually, users get this right more often. It's definitely more fun, although most of the apps have kind of shied away from this because it causes users to think that the app is not as serious. Even though you're representing maybe the same amount of entropy in just a different way, if it's a poem or if it's a bunch of hex, users actually get a much better feeling reading hex than they do reading a poem, because I don't know, I was thinking that maybe instead of having a poem with sort of flowery text like this, they need to make it seem like it's some top secret spy movie thing. What? Yeah. So I think, this is sort of a very marginal change to the experience. That's probably not going to solve the fact that most users don't want to do it.
Make a phone call and recognize the other person's voice.
Aha. You must have seen where I was going. So some apps do this. So if you have the voice channel available, you can read some fingerprint of the key. If you're online, you don't have to read a long fingerprint. You can do a short authentication string, so you really only need to have the person read about 30 bits. So that seems great. The user experience is much better. Users like it much more. It's very fast. The problem is that it's actually not secure. So there was a really cool paper at CCS a few years ago where they used voice morphing software. So if you have a very short sample of Alice's voice, you can quickly synthesize Alice saying whatever you want. And over the kind of fidelity of voice channel that you get in these apps, users fall for it every time.
Alice can get in when she has a cold.
What?
And Alice can get in when she has a cold.
Yeah, you can fake Alice having a cold. So.
Most voice recognition systems.
Oh, so there's no machine voice recognition here. The idea is that Alice is reading this short string to Bob, and then Bob says, that really sounds like Alice, so therefore there's no man in the middle here. So the recognition is being done by a human. But
this is not wartime, for instance, where people would be more paranoid.
Yeah, well, I think that's the real one of the real reasons that users fall for it so much is that you're not expecting the expected result is that you're talking to the person that you think you are, and your brain will basically map what you hear to their voice, even if it's off a little bit. So, I mean, I think they had some samples posted where you could hear, and if you're really listening critically, you can sort of tell that it's not quite right, but in real time, when you're not primed to expect that something's happening, your brain just completely fills it in, and people don't notice at all. So you could argue that this isn't the easiest attack to pull off. If you wanted to do this on a massive scale, you need to invest in a lot of resources to be doing voice morphing in real time for all these different users all over the place. But essentially, to a large adversary that we'd be worried about, a state-level adversary that was doing mass surveillance, the voice approach doesn't really work. There's been a couple of other attempts to kind of reimagine this. I'll just show a few seconds of this video.
Comparing it to the same.
The innovation here is that if you're doing this in-person exchange, rather than having people actually verify, let me see if I can full screen this.
Each phone calculates the same three-word
rather than
phrase
having people actually
along with
verify,
decoys
you do this
to encourage accurate
online,
comparisons.
synchronous exchange, and then
Slinging keys accomplishes
both parties
public key
check and see if
contact
either
card
of the things
exchange,
match, and then pick the ones
while also
the one
providing
that actually matched.
confidentiality and authentication against man-in-the-middle attacks.
And then that's kind of enough
And
to
don't
do the
forget
exchange.
to import your friend's secure keys.
So the interesting thing about that protocol that I really like is that the failure mode is not just that users click OK and then everything proceeds. You're not actually allowed to start talking unless the two parties both pick the same fingerprint that was shown on both screens. So if the users aren't paying attention, then the thing will fail because they won't pick the same thing. But unfortunately, I mean, you have to actually, this is still, I mean, it took them a 3-minute video to explain how to use it, so better than 12 minutes, but it's still a little bit complicated. And you have to actually meet the person in person to use this protocol. One other approach that has seen some excitement over the last couple of years is called Keybase. Does anybody have a Keybase profile? Oh, okay, so we have a couple of Keybase fans. So the idea behind Keybase is that you verify, or at least you gain some confidence that the key you have is correct. by linking it to some different profiles that this person has on the web. And there's actually a cryptographic pairing that happens here. So you get this big document, which is basically a proof that this specific key with this fingerprint here is owned by the same entity that owns all of these social media profiles. And you pair it securely by posting in these different locations. So to verify that this is really Max's Twitter account, Max is going to post this string, which is basically a signature under this key, sort of asserting that this key and this Twitter profile are linked. And then for different kinds of social media sites, there's different places where you shove this information. But the idea is that you're proving that the same person really owns all of these different things, and then the hope is that users can look at this and say, you know, obviously, like Max Krohn, the human being, is a little bit of a nebulous concept technically, but you can prove that it's somebody who owns all of these, and if you know Max and know that those are all him, then you might have pretty high confidence that this is the right key for the person that you want to talk to. But again, this is kind of a lot of work to set up. I think it's maybe a little bit more of a boutique solution than something that everybody in the world's going to do. So these are all different methods that you can try to do the key verification out of band. They all have the same weak point, which is that every time your key changes, you have to redo the process. So key changes are pretty painful. In Signal, every time somebody that you talk to changes their key, you get this warning message that says, you know, Bob's key is something different now. Do you still want to talk to Bob? Do you want to cancel? Maybe you need to re-verify.
Keybase from giving out a different PGP key for Max. Like the idea is that you as the user are supposed to go to Max's Twitter account and check that fingerprint matching.
So they like there's software that will do it automatically for you. Yeah, like it will fetch the right tweet and fetch all of this. So you get kind of this electronic dossier thing that, you know, asserts all of these pairings, and then there's client software that will actually sort of follow all the links and check all the signatures and assert that everything is actually legit. So the goal is that for the user, you just get this list here, and then you have to make the decision if these usernames are really the person you want to talk to. Yeah.
So is there any evidence that the decisions that people will make are going to be correct?
I haven't seen any. I don't have any evidence that it won't be. You know, Keybase is still a pretty new thing, so I haven't seen any research on A, if people can use it, and B, if people are able to make the right decision here. I mean, I think to me one tough part of this is that for a lot of users, they don't really have very recognizable handles. I mean, Twitter is one of the few platforms where people tend to know what someone's Twitter handle is, independent from their name or their email address. A lot of other things like Facebook doesn't give most users a handle that they really recognize. You know, to find users on Facebook, you search, and the search page kind of disambiguates. So, so I think it would be a great research project to see how well users do with this. Okay, so like I was saying, every time you change keys, it's painful. You get this message. You know, it's a pretty scary message for users. And I think engineers sort of tend to treat this as a detail to not worry too much about, because how often do users really change keys? It turns out that users change keys at a pretty high rate. So this is, I guess, from back in the TextSecure days that I got this data. But basically about 1% of the users of Signal change their keys every day. So that's kind of the daily turnover in the key directory at Signal, which is, it's pretty huge. Most people, when they first see that, say, like, why is it possibly so big? It turns out the market research on phones, the half-life of a phone, when somebody buys a mobile phone, the half-life is like 7 to 8 months. So really, really short. People just break phones a lot and they lose them. And a lot of people like to upgrade devices. So every time that happens, users usually change keys because they usually don't transfer the old keys to the new phone. Also, users just uninstall the app and reinstall it for kind of strange reasons.
So, a related question to that is, how many of those applications offer a method to either transfer directly from one instance to the other, or back up, quote unquote, the key and then restore?
Yeah, that's a good question. I'm not sure like exactly which apps do and don't offer backup. I know Signal does. I know that iMessage and WhatsApp certainly do. But you're sort of in a tough place because if you make the backups automatic, it's a security problem because then you're uploading everybody's private key to some server somewhere. And if it's a manual thing where you have to take the old device and the new device and pair it, a lot of people won't have the old device because it will be at the bottom of a lake. And even if they have the old device, a lot of people just aren't going to do it. So the assumption is basically users change device and they get a new key. Okay, so we've been talking about manually verifying keys. I'd propose that there's sort of this iron triangle of things you'd like with your key distribution system, 3 properties that are hard to have at the same time. You'd like it to be secure. You'd like it to be decentralized, so we're not trusting some central entity to behave itself. And we'd like it to be easy to use. So manual verification, not easy to use, but secure and decentralized. If you don't care too much about security, you can just do trust on first use, which means whatever key you first hear somebody tell you, you just kind of trust forever. That obviously is not very secure, because if you talk to the wrong person first, then you're sort of insecure forever. The approach that essentially all of these tools use in practice is they just use a trusted key server, which is easy, secure modulo the trust you have in the key server, but the trust in the key server is a big thing. So I guess I'll just say that there's a couple of different reasons that having a trusted authority to give out keys wins out in practice. You can deal with scale much better. You can deal with account recovery because they can just sort of mandate that you have a new key. In particular, you can do any kind of out-of-band recovery that you want. So the user experience, if you're an iMessage user, if you lose your device, you can show up at the Apple Store, down on University or wherever. They'll actually check your ID, or they'll verify, they'll do social security number or whatever kind of hokey security thing that they do, but they'll actually verify in person that you're still the same person, even if you've sort of lost all of your devices. And then they'll just, update on the server that your new public key is, whatever you want it to be. So, it's very hard to do this kind of out-of-band recovery if you don't have a trusted central server. Some other properties that I think are, people overlook. There have been a lot of attempts to do this using blockchains with systems like Namecoin, if anybody has seen Namecoin. Those systems usually fall apart because there's no way to deal with name squatting or people taking all of the good and interesting names. And if you have a trusted server, they can sort of do policing, and services like Twitter do this all the time, where they try to make sure that names really correspond to people, and if someone is taking a name maliciously, Twitter will take it back from you. Okay, so that's just sort of the quick case for why I don't think this model is going away. I think the main success we've seen is with apps that just have a central key server. So the technical question that I've been really interested in, that I've done some research on, is how can we ensure that this authority behaves correctly? So it's a little bit of a weaker goal. A lot of the time in cryptography, the goal is to remove third parties entirely and replace them with some cryptographic protocol. The goal here is to leave the third party in place, but use a little bit of crypto to try to verify that the third party is actually behaving correctly. This was the inspiration for a project called Connix that I worked on. And what Connix does is we say we want to leave the key server in place, but we want to sort of guarantee that it behaves consistently. And when I say consistently, the one property that we really want is that whatever the key server tells Bob, the key server also has to tell Alice. So Bob can ask the key server, what's Alice's public key? The key server can say whatever it wants. But whatever it says, it has to also say the same thing to Alice if she asks. Right? So the server can lie. It can be malicious. But if it lies, it has to tell the same lie to everybody. It can't equivocate to different parties. Okay, so why is that property actually useful? Now Bob knows that the server might be lying, but Bob doesn't have to worry about it. Bob can say if the server's lying, Alice will see the same lie, and then Alice can deal with the problem. She's better positioned to know what the server should be telling the world her public key is than I am. So I'm just going to take whatever the server says as the truth, and if it's wrong, leave it to Alice to figure out the problem. So now your client software only has to warn the users that something's going wrong if the server says something unexpected about their own key. So if if Bob's key changes, if you're Alice, your client, your software never has to warn you and never has to say Bob's key isn't what it used to be. The only time it ever has to warn you is if your key is something that you weren't expecting it to be. So the one warning message that you would get in a system like this this is a mock-up. This isn't well-tested UI, but you'd get some warning that would say the server has published some key that wasn't what I was expecting. Maybe you reinstalled the app or did something funny. If not, then there might be a problem with this server. The other great thing about this, besides the warning being simpler, is that you just generate a lot fewer warnings. So kind of in the old way of looking at it, without consistency, if somebody changes their key, you have to warn everybody else in the world that they talk to. So if they have n friends, all n of those friends will get a warning saying Bob's key just changed. But with consistency, you only generate one warning per key change because the only person who gets warned is the person who just changed their key. So that's the whole goal of this project, is to build a key server that we have some hopefully high confidence is behaving consistently, plus a lot of engineering constraints. So we sort of wanted this to scale. We wanted this to work with the way key servers work right now. There's privacy constraints, so I'll get into these constraints. And this work is sort of positioned in a lot of work that's happened in the last 3 to 4 years on this idea of transparency, which is sort of using servers that publish authenticated data structures that people can verify to see if the server is actually behaving correctly. So the most successful project in this space, sort of with this philosophy, is called certificate transparency. In some ways, that's similar. So you have this certificate transparency server that just maintains a log of all the certificates in the world. Sort of as long as you can audit that they're behaving consistently, you'll at least see attacks if they happen. So that's just to say, Connix is very much kind of inspired by this whole line of work. So the actual data structure in Connix, it uses what's called a prefix tree. It's an authenticated data structure. And periodically, the database changes. Every time it changes, the server publishes a signature on the root of this data structure, and clients are going to track these. Okay, so let's take a look at what this actually is. So this is the authenticated data structure. So this is the prefix tree. This represents a mapping from users to keys. The server assigns this root, so that's a commitment to the key of every user in the system. And then this signed root is what users actually track. So this epoch length, you might think this might be something like every minute or every 10 minutes. The server publishes a new one of these, which commits to the entire state of the database. You can see sort of over time this will change because users will come and go, users will change keys, etc. So the fact that each signed root includes the previous signed root, so that we're building a chain, this means that if the server ever equivocates, so if it ever tells two different people, if it ever gives them two different versions of the data structure, it's going to have to maintain this equivocation forever. So as long as the hash function is collision resistant, any equivocation the server makes, it's going to sort of have to maintain forever. So the server can equivocate, but if it does, it's sort of stuck with that equivocation. And then you have clients just audit for this. So if the server has published a different set of roots to Alice than it did to Bob, their clients can check, and this is totally automatic, so this is not an out-of-band check that Alice and Bob have to actually think about. Their software will just do this automatically, but they'll share the most recent root that they've seen, and if it's different, they'll know they have evidence that the server is cheating. And there's some other ways to do this too. It doesn't necessarily have to be clients talking. You can also publish this series of signed roots to some external log that's hard to modify, like the Bitcoin ledger, and then your client can check there too, kind of for extra safety to make sure that these signed roots that the server gave you are also published in this third-party log. And the assumption here, so all these clients are sort of auditing all the time, and if the server ever misbehaves, if the server ever equivocates, this is a really big deal, and we want the clients to be able to whistleblow. That means they sort of publicize this evidence to say, this server should no longer be trusted because it's behaving inconsistently. Technically, though, this introduces a couple of interesting questions. If you have some app and its only way of communicating with the world is through this key server, then it doesn't really have a means of whistleblowing. So it's important that your server can't be essentially your gateway to the entire internet. You have to have some way to communicate with the wider world that doesn't go through this central server. So, if you were trying to use this at the ISP level, the security argument would fall apart a little bit because that server could then, maybe reasonably prevent you from whistleblowing if it misbehaved. Okay, so if the auditing process works and we can trust that the server is not equivocating, everybody has a consistent view, then clients just have to monitor their own binding, their own entry in the database to make sure that it's actually correct. So if essentially for every version of the database, you'll get this reduced proof that just sort of shows what your entry is in the database. And if that's wrong, if that's some key that the server put in the database maliciously for you, then your software will pop up that warning I was talking about saying, the server has published some key for you that wasn't expected. Now we have to deal with the problem. So we tried to engineer this down as much as we could. I'll just sort of give you the high-level figure. We sort of simulated this for, if the entire population of the planet was using this system, you can do it, and the overhead is fairly modest. You're adding sort of, tens of kilobytes per day that you'd have to download to check that the server is actually behaving consistently. So we were. From a research standpoint, we were pretty happy with this. We said, yeah, you download like an extra 7 kilobytes a day, something like that, maybe even less. That seems like nothing. I've actually been surprised how many app developers I've talked to who said, like, we have users who downloading an extra 5 kilobytes a day will be like a real problem for. It seemed kind of crazy to me because I download all these apps that download megabytes worth of advertising without even asking me about it. But I guess, if I learn one thing talking to people who develop chat apps, they're very, very paranoid about bandwidth. That's like the main thing they worry about performance-wise is minimizing how much bandwidth the app uses.
You also have to worry about the guy who's been off the air for a month. Has to catch up.
Yeah, so I'll talk about that in a second. So I wanted to talk about the privacy concerns briefly. So the main privacy concern is that this authenticated data structure, if you do it naively, it will leak out the list of users who are using the system. So it doesn't sort of leak it directly, but there are attacks where you can sort of add users and you can do a binary search and you can figure out whether or not certain users exist in this tree. And you can see how these two versions of the tree, Alice will learn that she has a neighbor here because, Alice's inclusion proof in this tree will be one extra hop longer, so she'll sort of know some user, if this was the state of the system and it changes to this state, Alice will know some user that has a name that's close to me was just added. So information is basically being leaked here. So why would you care about that? Well, if you think like, what if it's an email system? Most email servers don't publish the entire list of users at their system, right? Because people are worried about spam. Maybe less so online today. Actually, I talked to the Gmail team about this back when I was working at Google, when this was sort of still the glimmer of an idea. And they were pretty confident with how much good work they've done on spam. They said, we think we've sort of won the war on spam at Gmail, and most users don't complain about spam anymore. And I said, that's great. So if we did this key transparency system, and as a result, we publish the list of every Gmail address, would that be okay? And then they sort of backed off, and they said, well, spam's a really hard problem. You're asking a lot of us here, so no. But I think that's fair that we don't want to reveal the list of all usernames in the system. So kind of classic trick, we just add a layer of indirection, cryptographic layer of indirection. So instead of actually inserting usernames into the system, we run the usernames through what's called a verifiable random function. So this is a cryptographic function, kind of takes any input, spits out some output, and it also produces a proof that this input-output pair is correct. And it has the property that you can't actually compute it unless you have what works out to be a private key. So, given this, it's fairly straightforward to solve the privacy problem. It turned out there were some engineering problems attached with this. When we looked around, we sort of realized that the VRF, the concept had been around for a while in the crypto literature, but nobody was actually doing it in practice. So there's a couple options here that didn't work for various reasons. They were either too slow or used crypto libraries that people didn't want to download. So with some help from Henry, we cooked up a new thing, and this is actually deployed in Signal now, which is kind of cool. We realized after this was pushed for the first time that this might be the first time people were using this crypto construction. I think it took about 15 years from the time it first appeared in a crypto paper to the time when someone was actually using it, which, if you look at the whole crypto literature, 15 years is like a reasonably fast turnaround, actually. So we fixed the privacy problem. Instead of actually storing a mapping from usernames to keys, we store mapping from these indices that are the outputs of from the random function. And then to actually check a binding, you sort of get that some opaque index x maps to a key, along with a proof that the name Alice is what maps to x. And then if you don't have this proof, it doesn't, you don't learn anything interesting if you know that x is in the database. Okay, so that's the Connix project. So the paper, I guess we wrote 2 years ago. It's now kind of an open source project. The Tor Foundation has released a messaging app called Tor Messenger. They haven't actually released their implementation of Connix yet, but they've been working on it. Google has, they've kind of adapted it and made some changes, but they're also doing a key transparency approach. I think it's exciting and to see that sort of people who are developing chat apps, they want to prove that they're actually reputable. Okay, so there was an ask about sort of the performance trade-off. How much work is it to do if someone's been offline for a while? So that is definitely the trade-off. There's a trade-off of how often you publish new versions of the tree. If you wait a long time between publishing, then it takes a long time for changes to happen. People have to wait to actually use their new key. But if you make it too short, if you try to publish them every second and you go offline for a month, then you'll have millions of these things that you have to go back in time and check. So there's sort of two performance hacks that you can try. One is to have this concept of promises, where you get a promise from the server that something will be in the next version of the tree, and then you can tolerate having a really long time between trees. So the way this would work, so Alice would say, please add my key. Bob is going to ask for Alice's key before it actually gets added. So, imagine that the tree is only updated every day or something like that. And then the server will respond, well, I have this pending new key for Alice. It's not actually in the tree yet. I promise I'm going to add it soon. So here's the key. You can, send a message to Alice now. So Bob gets the key and gets a signed promise from the server saying that it's going to be in the next version of the tree. And then the key is that Bob has to actually verify this later. So if the server doesn't actually put it in the next version of the tree, Bob will have proof that the server cheated. But of course, Bob has to actually wait around and check that. So I noticed a few people shaking their head and saying this sounds, maybe like a little bit of a weird security model. It turned out working with Google, they also really didn't want to do this because the engineering complexity of it was a lot. They have to track all of these different promises and sort of make sure they all get into the next version. So on paper, this is like a good solution, but in practice, it's a little hard to implement. So another approach that kind of fixes this problem is that you put a version number in. Every time you bind, a username to a key, you put a version number which says how many times that key has changed. And then as the tree is updated, like Alice's key got changed here, so now she's on version 2. So that seems like a really small change, but you can see how it actually fixes the problem now, because if you've been offline for a really long time and your version number hasn't changed, you don't have to actually go and check all the old versions, because you can just say, my version number is the same as it used to be, and as long as these version numbers can only go up, that means that your key couldn't have changed in the meantime. But this introduces this kind of tough problem that somebody has to be checking this property that version numbers are well formed, that they only go up. So somebody would have to be downloading the tree at every epoch and checking that the version numbers were all maintained correctly. If you like that model, the kind of natural extension is instead of just storing the versions, you can actually store the history of all previous versions of key that this user has had. So slightly more powerful, but same concept and same problem, that somebody has to go and actually check that this is all correct. Google's Key Transparency project is actually launching with this model. And their assumption is that sort of some good citizen on the internet will download the whole thing and check that the whole data structure is well formed. And as long as you trust that somebody is going to go do all that work, then the system is secure. And remember that if somebody is doing the auditing and finds that at some point a version number went in the wrong direction, they would have cryptographic proof, so they could publish it and say, look, something went wrong here. The server cheated and sort of messed with a version number. So kind of in the same way, when you audit for non-equivocation, if the server actually cheats, you get evidence and you can whistleblow and prove that they're untrustworthy. If the server, was cheating with the version numbers, you would be able to prove it. Another approach that I actually implemented last year as kind of a proof of concept because it was fun. You can do this whole thing in Ethereum. Which is a really cool, powerful cryptocurrency that's fully programmable. So it turns out you can actually write an Ethereum smart contract that does all of the checking for you. It checks the structure of the tree and checks that the version numbers go in the right direction. And then as long as the Ethereum system is secure, this sort of guarantees that the tree will be well formed. So this is kind of a cool way, rather than trusting that some random third-party person will do all this auditing for well-formed structure of the tree, you can have the Ethereum network do it for you. But you have to pay them. So computation in Ethereum costs money. Turns out it costs a fair amount of money. So it would cost on the order of pennies per day per user to pay the network to do this auditing for you, which isn't.
The whole system, right?
Yeah, but penny, I mean, if you have a billion users and it's a penny a day for each one, then yeah, then that adds up pretty quick. All right, so I wrote a large survey paper with some colleagues that sort of looked at all the different ways users could verify keys. And when we scored out the conic system, we said, wow, it really provides a lot of great properties. It's completely transparent to the user. It's sort of, the performance is good. It scales, all these other things. It sort of has almost every property that we want, but there's like a big hole here, which is that it doesn't actually prevent man-in-the-middle attacks. So you can sort of get all the usability and performance properties that you want, and what we've thrown away is that attacks are not actually prevented. So what the system, the property that it actually provides you is that if the server is publishing a key for you that's not right, you'll get this proof, and you'll say, look, your software will be able to warn you and say that the server is telling people your key is something that it's not. But you can't actually prove that to anybody else. You can say the server is publishing the wrong key for me, and the server can say, no, this is the right key. If you want, kind of the natural thing that crypto people propose is, we just need another key, and Bob will use that to sign every time he changes his key, and then the server can't change Bob's key without Bob's signature.
But then you have to distribute that key.
Yeah, exactly. So it's circular. The problem that we started with is that users are not good at managing keys. They lose them. So we said we're going to go for this weaker security model and use a transparency system. Then we had the problem that we can't actually prove misbehavior. And the solution that we know of is sort of make users manage another key, and then we're sort of back in square one.
Either when you upload your key, Google gives you a receipt that says Monday this is what your key looks like, and then on Tuesday you start publishing a different key.
Well, yeah, but the problem, so the attack would be like the server publishes a new key for you, and then they say, oh yeah, like actually Henry called us last night and he asked for a new key, or he came into the store and he showed us his driver's license. Then you can say like, no, I didn't, right? But they could provide a receipt that makes it look like it's you. Because remember, that was the user experience that we really want, is that users sort of lose everything, and then they sort of recover by some out-of-band mechanism that's inherently not going to be provable cryptographically.
Yeah, right. I was just going to say that right when you change your key, you sign it with your old key.
Yeah.
Right.
Yeah. So that like a continuity model, but users lose their old key, right? Like their old key is probably on a phone in a lake. Yeah. So we have to be able to recover from that. So I think it's kind of an open question. How much security does this really bias in the real world? Is this property that users will know if the server is cheating for them? Is that kind of enough? The claim is that this provides you with some reasonable hedge against mass surveillance. That if some intelligence agency wants to sort of update everybody's key to man-in-the-middle all traffic, that's probably not going to work, because every user in the world is going to get a warning that their key is wrong. And that's going to be enough evidence in the real world, not cryptographic evidence, but kind of human level evidence that this system is being backdoored. But if a few targeted attacks are made, a few users might be kind of complaining on Twitter and saying, I just got this message that the server changed my key and I didn't ask for it. That's probably not going to be enough to convince the world that the system's not trustworthy anymore. And there's always a few users complaining on Twitter about something. You probably will have some users complaining that the server is misbehaving even if it's not. So I would say as a kind of a caveat of this approach is that it's probably a good defense against the server attacking everybody, but a few sporadic attacks it's not going to produce compelling evidence of. Those users will still learn, but
With forward security, they still don't get the previous communications.
Yeah, that's true. Sure.
So one term that's come up before is security fatigue, and I understand that if some actor decides to try to man in the middle of a lot of people, then a lot of people are going to get alerts from their clients telling them, hey, your key has been changed, or what they say, see your key has been changed. Is there any protection to stop some actor from simply saying, okay, I'm going to have a server that's dedicated to simply flooding the network with new keys for every random identifier I can make, with the intention being that people will just get this message, hey, you've got a new key, oh, now you've got another new key and a new key, until they just get so tired of the thing alerting again and again that they just either ignore it or they go somewhere else.
Right.
In other words, is there a denial of service protection mechanism?
Yeah, no, this is a real thing, like a denial of attention. Yeah, I don't think so, because you only get warned if your key changed, and some random person can't change your key. Assuming the server is honest, some third party can't change your key, right? Like they need to know your password or your driver's license or whatever process you're going to authenticate to the server with. They can create a bunch of other identities and change keys, but the software won't warn you about that, right? So that was like kind of our whole goal, was to get rid of warnings in that case.
Instead of just using one server, why not use 3 servers in different countries and make them vote?
So you can. I mean, that might provide you something. I mean, it maybe gets a little bit harder then, because if you're doing some out of band verification after. Yeah. So the issue is like, if you have to go in person and show your. I know, but when you've lost all your keys, so when you have to recover. It becomes much harder to re-authenticate to multiple servers. So you either sort of have one server that does re-authentication, in which case they're kind of a trusted choke point, or it's a lot of work on the user to change their key at all 3 servers. Okay, let me just show a lot more stuff that I could say about conics and other things. Let me show you one other thing that has been instructive for me. So there's another really big challenge is communicating to users what security properties different apps have. So I spent a lot of time at EFF working on this project to have a secure messaging scorecard where we would show different applications and try to summarize their security properties in a really simple way for users. So we workshopped this for a while, and we ended up coming up with 7 criteria here that we would evaluate for different apps, and then we had a very simple scorecard with checkboxes for different apps, and we published this on the web, and the goal was to give kind of a very rough scorecard on how different tools were doing. So you can see the different properties here, and we tried to make them simpler by not using crypto jargon. So we didn't talk about forward secrecy. We said, are your past communications secure if your keys are stolen? And we didn't say end-to-end encryption. We said encrypted so the provider can't read it. It turned out, I can admit now this project was kind of a failure on 2 fronts, which is a little sad. The security community felt like this was a gross oversimplification, and it gave people kind of too much confidence in some apps. There were some apps that people thought were insecure, but yet hit these 7 boxes, and they said this shouldn't be getting a perfect score because it's not a perfect application. The security community felt like this was too much of a simplification, and we should sort of ask more of users that give them more information. And when we showed it to users, so I just finished a year-long project with some colleagues in the UK. We did 60 hour-long interviews with different users where they talked about all of their secure messaging habits, and they sat down with the scorecard and read it and tried to understand it. And the conclusion was that I think of the 60 users, basically 58 of them didn't understand it at all, and 2 of them understood about half of it. And not only did they not understand it, but their understanding was exactly opposite of what we wanted for parts of it. So all of the users thought the code being open, proper design, and code audits, they all thought that these were negative properties. So they thought that the app would be less secure if the code was open to outside review. So I guess it makes sense, but I mean, it was a little disappointing to see that the general public still definitely believes in security by obscurity.
Why say open? Why not just say verified by security professionals? Open is you knew that open was a bad word when you started, yet you used it anyway.
I didn't know it was a bad word. Maybe maybe
did.
what?
You did. Because it's always been a bad word, because you're not that young.
I don't know. I mean, I feel like on the web, open is, people are always putting open in front of stuff. Is it good?
Oh, yeah. Uh-huh.
Yeah.
Some people may think that open means writable.
Yeah.
Yeah.
So yeah, I mean, I don't disagree that it was a bad choice, but to me, it seemed like a good choice at the time.
The whole bit of, outside the geek community, open source is seen as, oh, no, you want to be secret inside Microsoft.
Yeah.
But see, you knew it.
What?
You knew it. You knew that was your mother's right reaction. Well, your mother might be different, but your neighbor's mother.
Maybe I overlooked it.
Yeah.
So this sort of bottom half here, the sort of openness, which are sort of, we thought were good signs of project health. People didn't like those.
Good housekeeping seal of approval.
Yeah.
Which could be completely closed.
Why is it so complicated? Why isn't it just a green check box or a red X?
Well, because there's sort of no perfect app, so we didn't really know what we would give the checkbox for, and then give an X to everything else. So, but the even sadder thing. So users didn't understand. They didn't know what encryption meant at all. Actually, when we asked them. Most users, when we described encryption, they basically described encoding. So they said encryption is the process of taking the text and turning it into ones and zeros so that it can be sent across the wire. So I'm like completely serious. Over half the users thought of encryption as basically, looking up the character code in UTF-8.
Also, you use the word wire.
Sort of belies real processes.
Yeah. So users didn't understand it, and when we explained what we meant, the users completely rejected the notion that end-to-end encryption was even possible. So we basically we said end-to-end encryption is a way that the only people that can read the data are you and the person that you're talking to, and Google or Apple aren't actually allowed to read it. And people just stopped and said, I don't believe it. They said, there's no way that's possible. I know that they can read everything. Apps can't provide that property. And the appeal to experts, saying sort of scientists have been working on this problem and cryptography can provide this, people just refused and the interviews ended and people went home. So it was actually really disturbing to me, kind of deeply as a crypto researcher, to realize that the general public is kind of so far from understanding what we're able to do.
Controls the operating system. Can't they see what the app's doing?
Yeah, so you could argue that maybe the people are slightly more, something to it there, but we asked a bunch of follow-up questions and that's not what they were thinking.
Some of your customers may not believe that Apple has distributed to their computer a program that does what they say it does. In that case, Apple could read.
Yeah, so I mean, that's the same point. So we were worried about that, so we asked kind of follow-up questions, and there were 1 or 2 people who sort of made that point with Apple specifically. They said Apple owns the phone, so they control everything the phone does. But most users, when we actually pressed, that wasn't actually what they were getting at. It was kind of amazing. They just fundamentally didn't understand how encryption. Yeah. So I guess I'll just conclude, and then I can take some more questions by saying, there's still, I think what's a really big problem is, a really big open challenge is figuring out a way to kind of open people's imaginations a little bit, and show that crypto is possible and that it can do good things, and that there are kind of technical safeguards against surveillance. This work definitely made me realize that we're much, much further away from that than I imagined that we were. Yeah.
Probably worthwhile pointing out that cryptographers are not singled out by the general public as being people not to believe. Most scientists are singled out by the general public as being not to be believed.
But I thought cryptographers had I didn't think that the public had any reason to be skeptical about cryptographers. There hasn't been a big political campaign, like with climate scientists, to say that cryptographers are charlatans, right?
Not so certain that that's even an issue here. It's the reasons behind the rejection of science probably have very little to do with reality.
Yeah. Yeah.
I was going to say, then again, people like Target and Home Depot probably have done a pretty good job of destroying the reputation people think of as cryptographers, right? Computers are all insecure. They don't know what they're doing.
Yeah, that's definitely true.
This all, of course, presumes a uncorrupted platform to run on.
Yep. Yeah, I mean, I said at the beginning, like if we don't have secure software, then nothing's going to work.
What's going to happen to your scorecard in the face of the Investigatory Powers Act?
Well, I mean, the scorecard's not going to, yeah.
Banned in England.
What?
Banned in England.
Well, the scorecard's not going to be banned.
Yeah. Can't get this check mark in England. Can't get this check mark in Latvia. Can't get this check mark in Hong Kong.
Yeah.
Can't get this check mark in Boston.
But that's a new way of rating things. Is it banned in England? That means it must be good.
We are redoing the scorecard, and it's going to relaunch in the spring. And we realized that, this was not working. So the new format is going to just basically have tiers and say, like, these are good apps. These are sort of, it's going to be sort of like a good, better, and like avoid.
What about underwriters' laboratories? Somebody else mentioned this. That's a certification that the materials used in the construction of a device don't burn, basically. And maybe that's something that you might do better with a EFF or CryptoSafe or something, seal of approval, which basically summarizes the 7 points here in a totally obscure form, but the reputation of the group producing it is carried forward, and it might work a lot better.
Yeah, I guess it's not clear to me who that party would be. I mean, for some in the tech community, they really trust EFF's opinion. So the scorecard did get, it was getting millions of page views every month. And, in some sense it was popular with a certain group, but sort of globally the EFF brand name doesn't mean so much. I mean, I'm not sure Underwriter Labs means much to the general public either. Yeah, Consumer Reports, I guess, would be it, but even...
The issue with the UL mark is that when you look at consumer devices, you design them, you manufacture them, and then they're locked in, and they're manufactured over some period of time. If you extended that to software, you'd have to redo the entire process every time you updated the software, because you don't know what's changed, or if a small change has had a big effect. One thing that might be interesting is looking instead of looking at the product, look at the source, look at the people who are making it. By which I mean there's already training standards and licensing standards for people like architects. You could move that same type of thing into the people who are making the software that you want to trust, just like you're doing certification requirements for the people who make the buildings that you're going up to the 50th floor on.
Yeah, I mean, I guess my response to that would be, some of the most widely used crypto in the world that I think cryptographers would really vouch for, whether it's Signal or something like Curve 25519, is written by people who probably wouldn't have qualified for a certification and would have actively refused to sit down and get one. I mean, I'm serious. Like, the crypto is often developed by people without formal credentials. I mean, Signal in particular, like, Signal is usually the app that people have the most confidence in, and the main developer of Signal is a self-taught cryptographer. So I guess I'm not...
Well, you could just certify it, not ask them to sit down, just certify it.
Okay.
And if you're looking at like an architect didn't create the steel that's going into the building. He's just taking the pieces and putting them together in some hopefully safe way. So I'm not ever going to design Curve 25519, but I'm hopefully going to use it in a safe way that doesn't just completely break everything.
If you talk to Consumer Reports,
There was, at one point, I think, some thought about that, but I think there was like, they sort of wanted to have copyright and sort of limit who could look at the scorecard. So, you know, EFF wanted to do some public thing that we could put on the web and everybody could, I mean, Consumer Reports is like a company and they sell to subscribers, so it's like a business model clash.
There have been efforts where the government has almost tried to tar encryption as being unpatriotic because terrorists use it, and you know we need to, in order to protect you, we have to know what you're saying secretly. Has that had much penetration into the public psyche where they think that what you're aspiring to isn't even a good thing?
No, I mean, actually, I was like, that didn't come up that much in our interviews. There wasn't much of like a negative perception of encryption. People just, they didn't know what it was or what it could do, but yeah, I guess I didn't really see it. I mean,
also, in decades past, there have been government agencies that were very well respected as being technically competent. The NSA used to be, you know, so special and magical and above reproach, they seem to know. NSA knew what they were doing, and they were really good at their jobs. That's probably suspect now, but
I think actually, I mean, it's interesting having, I went to grad school in the UK, so, you know, I spent a lot of time there. The UK public has a much more positive relationship with its intelligence agencies than I think the US does. They have kind of they also have kind of a revered place in British society dating back to Bletchley Park and the war. Yeah. So, yeah, I mean, I think they do have a pretty good reputation for competence in the UK, which, you know, might explain why the UK has been able to pass much more aggressive, you know, surveillance laws.
well, I think the NSA still has a reputation for being extremely competent, but maybe suspect in their intentions to the extent that they might be trying to sneak back doors into something. I'm not sure even I would trust the NSA wasn't. An endorsement by them might be proof of there being a weakness of some sort.
Right.
What about specialized populations, namely reporters and lawyers, both of whom have good reason to worry? What's their uptake and what's their approach? They all use Signal now?
Yeah, a lot do. So, you know, EFF works with those groups a lot. We published like a whole series of docs called the Surveillance Self-Defense Guide that walks through exactly how to install, you know, not just secure messaging tools, but things like Tor or the Tails operating system on different platforms. So yeah, I mean, there's a lot of outreach to those communities. And
Are you getting uptake?
yeah, Signal is really popular among journalists now. I mean, and it's even, I mean, actually the anecdote is that the Hillary Clinton campaign switched from email to Signal internally in about September.
Just in time.
Well, they were getting killed by email leaks, obviously.
Yes, that's right.
But so they're, like Signal has, it's got some pretty dedicated users among a couple of different activist communities. And
so is that the first thing that the government will go after in January?
Signal?
Signal.
They might. I mean, they've already, sent one legal request to Signal. So yeah, it's possible, but I don't know. The Trump administration, that a reporter asked the EFF, a reporter asked EFF what we should expect from the Trump administration with regards to surveillance, and we actually have no idea. So, I mean, I wouldn't say people are hopeful, but there isn't like a long track record of statements on surveillance or tech policy in general from Trump, so it'd be interesting times probably.
Is there any serious concern about hardware being compromised? Because I was recently at a talk where someone was proposing to have a system where you have completely verified hardware running completely verified software. Is that anything that people need to seriously think about?
Yeah, I mean, I think there's definitely like concern about, yeah, I mean, yeah, like
is my iPhone compromised?
Is your iPhone compromised? Yeah, I think there are. I mean, depends on your definition of compromised, but yeah, like I think it's not crazy to think that certain things, may be there. So that definitely I don't know. The way I view it, though, to answer your question is, we should get the software right, and then if the software is all right and the attack that people are forced into is that they have to actually compromise the hardware, then we've sort of won something, right? If you don't even have to go after the hardware because people are all running insecure software and not encrypting, then
it's highly likely that the software or the hardware is pretty compromised at this point.
Yeah, I don't know about highly likely, but it's within the realm of possibility.
X86 has lots of holes.
I mean, it used to be the case that the baseband had DMA access on most phones.
Right.
And so, well, it's actually changing a lot. Recent phones, it's just a peripheral that's essentially connected via USB. Right. I mean, to first order. So that's a significant improvement. Yeah, we might be willing to say something like the very first iPhone was pre-compromised in the sense that the baseband could do anything it wanted to.
Right. Sure.
Are foreign governments starting to audit these things against other intelligence agencies? Like
audit.
Are foreign governments like China starting to audit iPhones, for example, against foreign intelligence agencies spying on their citizens?
Oh, so you're asking, like, is Chinese intelligence auditing iPhones?
The Chinese government, the cybersecurity services, saying, we'd like you, the foreign company, to show us that some foreign intelligence agency isn't doing mass surveillance of our citizens.
Not that I know of. Yeah, I don't know. I haven't seen any evidence that the Chinese government is like specifically auditing phones or asking to see. I mean, there has been a lot of concern. There's been a lot of talk about people, especially in Europe, wanting to move data centers out of the U.S. and not rely on U.S. services.
On China 3 months in June.
Oh, interesting. Yeah, I guess I don't know the Chinese situation so well, so I probably can't say very much.
Cool.
All right. Thanks, everybody. Okay, so yeah, I'm currently a postdoc here at Stanford. I'm also a technology fellow at the Electronic Frontier Foundation. So I'll be talking some about my academic research and also about some of the work I've done at EFF to promote secure messaging tools to try to help people understand different secure messaging tools and what properties they provide. So the context of all this really in the last couple of years, we have some good evidence from, I mean, there's tons of anecdotal evidence, but there's also hard evidence from talking to people that people are much more concerned about surveillance than they used to be.
Yet they use Facebook.
Yeah, but this shows up both in surveys and also from the EFF's perspective. After the Snowden revelations, the EFF got tons and tons of queries from all sorts of different organizations. They said, "What can we do to protect our communications from surveillance? What can we tell the dissidents that we work with? What can we tell the journalists that we work with about how they can protect their communications?" So this has been a really, really big topic. I think there's some evidence that people don't totally understand what the real threats are. If you look at data from this same survey, people are much less worried about using a landline phone than they are about sending email, using chat or IM, which is what I'll be mostly talking about today, is sort of chat or IM or messaging tools. So people don't exactly understand what's going on because they still think that using a landline is secure here. It's really not. I mean, this is probably the least secure of all the communication channels here. I would say, using a plain old telephone system is basically the worst you can do. There's no encryption, or there's no real possibility for end-to-end encryption. So if you're worried about kind of government surveillance, this is, not a great place to be. So I'll come back to this theme later, that users don't exactly understand what they're afraid of or what security properties different channels have. But for now, I just wanted to say that people are definitely more worried about surveillance than they have been. So the high-level bit that came out of the Snowden docs that was positive is that there was no evidence really that they added after the fact, and they were able to add in end-to-end encryption, which we saw for email as sort of this cripplingly difficult thing to use. They were able to do it without even changing the user experience. And there are a whole lot of other apps that have launched that offer some level of end-to-end encryption, including, I know it's really confusing because almost every one of these apps has some version of the same logo, which is a chat bubble with some kind of lock on it. But this is Facebook Messenger, which also has hundreds of millions of users, and this is Google's new Messenger, which is supposed to replace Google Hangouts. So Facebook and Google have sort of gotten on board the end-to-end encryption train. Although it's important to note there's a big difference in that Facebook and Google users have to actually explicitly turn on the end-to-end encryption. So they have to choose to have what's called a secret chat. Whereas with WhatsApp and iMessage, everything's end-to-end encrypted by default. You don't have a choice to fall back to insecure mode. So it's interesting that they've differed there.
Signal play in this race?
So Signal, which happens to be right here. So I'm sure a lot of you have heard of Signal. Hopefully we have a lot of Signal users. Signal, it has, the order of magnitude that we're talking is about 1 or 2 million users. So it's at least 2, maybe 3 orders of magnitude smaller. I think a good way to think about Signal is it's kind of like a Formula One car in a way. It's kind of pioneering the new technology. And in fact, Signal's encryption protocol moved from Signal to WhatsApp. So Signal is sort of more cutting edge. They're adding more features and sort of experimenting on security, but it's always going to be kind of a smaller user base because it's a security focused thing. It doesn't have as many of the features that users like for fun, kind of emojis and sharing animations and things like that. So that's how I view its role.
How vulnerable are big players to something like the Investigatory Powers Act?
So I guess the rest of this talk will be sort of talking about that a little bit from a tech perspective, from a legal perspective. I'm not a lawyer, so that's a pretty complicated question. I think even the lawyers at EFF have been thinking about for a while, and it's really not clear. I mean, obviously through EFF we were involved in a big fight over iMessage that wasn't about Apple. It wasn't about iMessage specifically. It was about encrypted devices. But anywhere in the docs, besides a couple of things kind of circumstantially that people have patched in, there wasn't much evidence that the main cryptographic protocols we have are actually broken. In a few places, there was actually evidence that NSA was frustrated when people were using PGP because they didn't actually know how to decrypt and read the messages. So when people use cryptography, from everything we know, it still works. It doesn't appear, even that NSA has a magic way to break the good cryptography that we have when it's actually used. So the problem, of course, is that it's famously really hard to actually use cryptography. So how many people have used PGP? Okay, so most people, so Henry's a holdout there.
It is hard to use.
Yeah. So I'll just show you a couple clips from this video, which I think, if you've never seen this video, I think really drives the point home really well. But this video was actually made by Edward Snowden and given to Glenn Greenwald, the journalist that he was working with. And Glenn Greenwald said, at the beginning of his conversations with Snowden, he really didn't know anything about encryption or security, so he had to get up to speed to rendezvous with Snowden and kind of serve as his liaison to the public. So you'll notice this video is going to be 12 minutes long. So right off the bat, if it takes 12 minutes to explain to the public how to use a piece of technology, that time budget is kind of way too long.
It says, hey,
so you can see, so it's kind of a fun video. Snowden actually used some voice masking technology here, which is why it's hard to recognize his voice. That was by design. So anyway, he spends some time kind of talking about the threat model. And then he starts walking through how to actually use PGP software on Windows. And it's really a mess. I mean, you can kind of look along the bottom of the screen here. At the beginning of the window, at the beginning of this video, it's just the web browser that's open, and it kind of slowly builds up. By the end of the video, he gets, almost his entire system tray here full of applications that he's running. So there's like a lot of stuff going on. At this point right here, he's now creating keys, kind of 5 minutes into it. And there's one point, let's see if I can jump to it, where he's actually, copying keys. Okay, so, I basically told you that PGP is mostly dead. I think very few people are really even trying to revive it at this point. I mean, it's still very much alive and that a lot of people have used it, but I think we have pretty clear evidence that it's sort of not the mass market solution that people hoped it would be.
What's the largest percentage of anybody that you communicate with of messages they sent out encrypted as opposed to clear text?
You're saying in my personal communications?
In terms of anybody you've ever encountered. I've never found anybody who sent more than 10% encrypted communications, if that high.
It's a good question. I mean, I guess there are some, I don't know about people, there are some email addresses that are always encrypted, but in terms of like an actual human being, I don't know. I think most people will have an unencrypted email address for sort of, signing up for accounts and maybe emailing friends, small stuff. So, I would certainly agree with your statement there that most people don't encrypt very much of their email over PGP, even if they use PGP. Okay, so the scene for PGP is kind of grim, but at the same time, in the last few years, we've had a somewhat quiet but a revolution in how much end-to-end encryption is actually happening. And all the action is happening on chat applications or messaging applications, basically software that you download on your phone that gives you kind of an ephemeral chat experience. And the two biggest ones, iMessage from Apple and WhatsApp. So each of these apps has a user base that's in the hundreds of millions to billions of users. And everything is now end-to-end encrypted all the time. So in human history, these are by far the majority of encrypted communications that have ever happened have been over WhatsApp and iMessage. Just the amount of encrypted traffic that's gone through those two systems is vastly more than the amount that ever went through PGP in its entire lifetime. So I'm Is everything okay? Okay. Yeah, so in a sense, that's really exciting. And I think the most interesting thing is that most users who use WhatsApp actually don't even know that it's encrypted. And the same thing is true for iMessage. So it's kind of completely transparent to the users that are using the app, but everything is encrypted now. In fact, until about a year ago, WhatsApp wasn't encrypted, so this is something that he's using Notepad, he's copying and pasting the key in ASCII just to import it from the tool that created it to the email client that's going to actually use it.
And you just click encrypt.
There's parts in this video where he says, oh, like, you have to hit that checkbox or else the whole thing is insecure. There's kind of gems throughout, but it's a pretty clear sign that this PGP is over 20 years old now, I guess almost 25 years old, and it's never really grown into a technology that people were comfortable with using. So we have a lot of evidence for that claim beyond just one video. The video is more fun. There are also a lot of academic studies in the lab. They brought users in and given them tasks to say, can you install PGP software? Can you communicate with these people? A lot of people just don't do it at all. It just blocks their communication. A lot of people will, in those experiments, they'll inevitably send things out in plain text. They'll do things like, encrypt to their own public key and then send to somebody else. So, we have pretty hard numbers that this doesn't work so well in practice. And if you need any more convincing, this was maybe the most fun anecdote from my time at EFF. I was working with Phil Zimmerman on a project. So Phil Zimmerman was the original developer who created PGP. I made sure the first time I emailed him that I PGP encrypted the message, and he just responded in plain text, sorry, I don't do PGP anymore, so just send this back in plain text. And I asked when I got this, I said, you have to let me use this in talks and tweet about it, because this is so perfect that even the person who made this software found it too unusable to actually use. So that's kind of the state that we've been in for a while, where cryptographers have historically not devoted too many resources to this problem. There's a by now pretty famous paper that was written last year called The Moral Character of Cryptographic Work, arguing that the cryptographers sort of owe more to society than to sort of ignore and marginalize this work on making things actually easy to use. To be honest, I'm not sure this paper has really swung more researchers to get into this problem. I think it's gaining a little bit of traction, but it's been a real problem to get cryptographers, especially in the academic setting, to stop sort of, or maybe to not spend all their time chasing the next big algorithmic or theoretical breakthrough and try to make the things that we've had forever actually easy and secure for people to use in practice.